Assalamualaikum warahmatullahi wabarakatuh. My name is Nur Danyana Binti Rasli from Faculty of Electronic Engineering from Section 1 for Computer Architecture and Organization. And I'm from Group 10, and this is my group partner No Akmal Azur Binti Rosnan CE210054. And I will explain about the introduction of YOLO, methodology, and conclusion. So, YOLO, or You Only Look Once, is a popular object detection model known for its speed and accuracy. It was first introduced by Joseph Redman in 2016 and has since undergone several iterations. The latest being YOLO v7. Modern-day object detection algorithms such as You Only Look Once heavily uses convolution layers to learn features as an object passes through convolution layers. Its size gets reduced. Therefore, the small object disappears after several layers and becomes undetectable. Following a fundamentally different approach to object detection, YOLO achieved state-of-the-art results, beating other real-time object detection algorithms by a large margin. Several new versions of the same model have been proposed since the initial release of YOLO in 2015, each building on and improving its predecessor. YOLO divides an input image into an S times S grid. If the center of an object falls into a grid cell, that grid cell is responsible for detecting the object. Each grid cell predicts B bounding boxes and confidence scores for those boxes. These confidence scores reflect how confident the model is that the box contains an object and how accurate it thinks the predicted box is. YOLO predicts multiple bounding boxes per grid cell. At training time, we only want one bounding box predictor to be responsible for each object. YOLO assigns one predictor to be responsible for predicting an object based on which prediction has the highest current IOU with the ground truth. This leads to specialization between the bounding box predictors. Each predictor gets better at forecasting certain sizes, aspect ratios, or classes of objects, improving the overall recall score. For the second part, which is methodology. Okay, the first one I will explain about the flowchart. So, after we start, then we choose the image, our image pumpkin, and then we train the image. After that, we make the images annotation. After the image annotation, we need to do the annotated the dataset. After that, the dataset will be processed, and then we do the YOLO training. After the YOLO training, we evaluate training models and then training objects successful. And after training objects successful, if not, we need to return to the dataset processing. Then we need to run again. If yes, the image will detection. And that after successful, then it's end of the flowchart. Next, project's procedure. Our assignment theme is vegetable, and our group choose pumpkin as our object of interest for annotation. Our team search for image on the Google platform and collecting 200 images. RoboFlow is a well-known platform for gaining access to and sharing datasets for data science and machine learning projects. RoboFlow is a database of publicly accessible datasets that anyone may access and utilize for a variety of data analysis and machine learning applications. So, as you can see, the figure number 2, this is the process of export dataset from RoboFlow. Then the figure number 3 is dataset in the Google Drive. After that, the next figure This is we import a Google Drive dataset, specify the root and install Ultra Lightstate. Then we train the model. After we train the model, then we need to copy the result and save file result.
Hello, my name is Nur Akmal binti Rosnan. My matric number is CE210054. So I will explain for the result and analysis that my group gets. Okay, first this is the result for 5 epochs. This is for label image, and this one is for prediction image. Okay, this is for 10 epochs, and this is result for 20 epochs. Every epoch we get a different result. This may happen for a variety of reasons, include indicate lightning or impediments, and mistake include both false positive and false negative, which are examples of model identification errors. As you can see, for the prediction, for this one is 1.0, this one 0.9, this one 0.7. Then the data agreement and obtaining more diverse data carefully analyze the mistake and maybe altering the model architecture. But we can improve the performance for our model to get the less prediction of image. Next, this is the precision confidence curve graph that our group gets. From 0 increase to 1, and this is for precision recall curve. From 1 decrease to 0, and this is for recall confidence curve. From 1 then decrease to 0 also. This is the loss graph for epoch 5. This is loss graph for epoch 10. And this is the loss graph for epoch 20.
Lastly, for the conclusion, modern object detection algorithms like YOLO are renowned for their accuracy and quickness. For every object in an image, YOLO predicts bounding boxes and class probabilities in a single stage using a single convolution network or CNN. Because of this, YOLO is significantly faster than other object identification algorithms, which usually employ a two-stage methodology that entails classification and region proposal. Apart from the previously mentioned benefits and drawbacks, YOLO is also very generalized. This implies that substantial retraining is not required when applying it to a variety of domains, including nature photos, artwork, and medical image. All things considered, YOLO is a strong and adaptable object detection system. In the end of this project, we understood how to use Google Color to identify an object in an image. Google Color aids in the learning of tasks such as 3D data annotation, image segmentation, object detection, and image classification. Furthermore, we also use the cloud computing platform YOLO version to process the image of the desired object that we have identified in any cloud computing database. And that's all from me. Thank you.